Honors Algebra 2, Chapter 8, Section 2 and 3. So they're both dealing with graphing rational functions. The first one, so we're looking at functions that have a fraction where the numerator and denominator are polynomials. So the graph is a hyperbola, whenever you have this, which consists of two symmetrical parts called branches. Typically for the parent function, I would have like this, two branches. Now last chapter we talked about asymptotes. These also have asymptotes, which will have a vertical and horizontal some of the time. So we have some different kinds of asymptotes here for these types of graphs. So how do you graph one of these equations? 8.2, we first start with the simple one, the rational function in this. The graph is a hyperbola whose center is hk. So the center is the center of the asymptotes. Center is the center of the asymptotes. So to graph this, we want to first draw the asymptotes using h and k. Then we want to plot points to the left and the right of the vertical asymptote to draw the two branches using the asymptotes and the points. So that's kind of a plan. And so given this equation, knowing that our h is actually positive 1 and then our k is 2, I look at those values. H is 1, so we have a vertical asymptote at x equals 1. We shifted the graph right 1, and then up 2, so plus 2 would be a horizontal asymptote. And so that's kind of like our new x and y axis you can think of. We kind of shift the graph right 1 and then up 2. Then when we're graphing this, we can then start plotting points. When we make our table though, I'm going to be choosing x values that are on both sides of this asymptote. So I'm going to look at 2, 3, 4 and figure out what's happening. So 2, 3, and 4. So I'm plugging it in an equation. So I plug in for x. So 2 minus 1 is 1. Negative 3 divided by 1 is negative 3. Negative 3 plus 2 is negative 1. So it'll be 2, negative 1. So you can kind of see the shape here, and I can use the asymptotes to help me sketch a curve here. And then I plug in the x values of 0, negative 1, and negative 2 into the same equation to evaluate it. If you do that, you would find values of 5 and plot these points, and we can sketch the curve using the asymptotes to help us get our curve. We're approaching them, but never crossing them, never touching them. So this would be the shape of our two branches. So this will be your turn, this will be your video problem. Give this a shot, same kind of process. So sometimes our rational functions are written as a single fraction like this. Or we start having some polynomials. This is a binomial in the numerator and denominator. So when this occurs, we have to recall that our denominator cannot be 0. This is what creates our vertical asymptote. If I set x minus 2 equal to 0 and then solve, I'll find x equals 2 as a vertical asymptote. So our horizontal asymptote, we start having rules for some of these, for these rational functions. Our horizontal asymptote, we have some rules about these x points here, x to the first, x to the first, that when those are the same, we actually look at the coefficients in front. And so the horizontal asymptote is actually y equals 2 over 1. That's going to be the horizontal asymptote, which is just 2. And then we can plot some points to graph this. So if I draw that, x equals 2, this is my vertical asymptote. Y equals 2 is my horizontal, so they happen to be the same value. And then like before, we plot some points on both sides of the vertical asymptote when we plot the points. So we can make our table and plot some points on both sides of x equals 2. So plot 3, 4, and 5. And then 1, 0, and negative 1. So here are the values we get when you plug in these x values. If I plot those, we have two branches. So recall we have two branches when we plot these. So there's 3, 5, 4, 3.5, 5, 3. And I can sketch the curve approaching the asymptotes. And the other one should be down this quadrant to get this shape, the curve. And so that would be the two branches for that graph. So knowing how to find the vertical and horizontal asymptotes. 8.3 breaks off of that. So 8.3, these are the rules for all rational functions written in the form where you have the polynomial in the numerator and a polynomial in the denominator. And so that's what 8.3 is talking about here, is let p of x and q of x be polynomials with no common factors. So you've already kind of factored it down, other than positive -1, so it's like the prime factorization. The graph of the following rational function has the characteristics listed below here. So the x-intercepts of the graph of f are the real zeros of p of x, which is our numerator. P of x is the numerator. This occurs when you have a fraction. The only way a fraction, if I have this be like m over n, the only way that this fraction is going to equal 0, the only way it would equal 0 is if the numerator equals 0. Our denominator can't equal 0. So our numerator, we only care if m equals 0 will tell us when y is 0. Number 2, the graph of f has a vertical asymptote at each real zero of q of x. Basically, set your denominator equal to 0 to find the vertical asymptotes. And then our horizontal asymptotes have these rules. And we kind of talked about one of the rules in the previous problem, that if you're looking at m and n are these exponents. When you look at those exponents, when they are the same, m equals n, the line y equals, you divide the coefficients in front, is a horizontal asymptote. And that was like the example we just previously did. We have two other situations. What if the exponent in the numerator is less than the exponent denominator? So you get x squared over x cubed. Then the line y equals 0 is a horizontal asymptote. It's always going to be the x-axis. If m is greater than n, then there is no horizontal asymptote, but there could be something called a slant asymptote, and we'll briefly talk about that. This occurs if the degree of the numerator is 1 bigger than the denominator. So some examples here. For this one, we need to be able to state the domain and the range, and you should be able to pull that out of the equation fairly quickly. So first, let's look for our x-intercepts. Our x-intercepts is when the numerator is 0. Okay? The numerator is 0. So we can't have the numerator 0 because it's 6. So there are no x-intercepts. We can look at the vertical asymptotes, and to find the vertical asymptotes, we look at the denominator. We take our denominator and we set it equal to 0. We solve for this. We're figuring out really what x cannot be. So I square root both sides. I find that x equals plus or minus I, imaginary. So since it's imaginary, there really are no vertical asymptotes. So we have no x-intercepts, we have no vertical asymptotes. So we have a horizontal asymptote. We look at the degree of the numerator and compare it to the degree of the denominator. The numerator right here is x to the 0, you could put if you wanted to, so just 1. So the numerator is smaller than the denominator. So then our horizontal asymptote is y equals 0. The x-axis is the horizontal asymptote. So then to graph this, we just literally need to plug and plot some values. So if I just choose some here, let's put in this. So it's going to be 6 over our x value squared plus 1. So this is going to be 6 over 10, which is 3/5. If I plot these, and so it's going to approach our asymptote. So we come up to this top, and I curve back down. You can get to the beach there. Curve back down and flatten back out to the asymptote. So that would be the shape of the graph. A second one here, now we do have the polynomial on the numerator, we have some exponent. We can find our x-intercepts here. Again, we can look at the numerator. So we say 2x squared equals 0. And so this would be x equals 0. So I know when x equals 0, it's going to be an x-intercept. It's the only x-intercept. The vertical asymptote, we look at the denominator, x squared minus 9, set it equal to 0. we should be able to factor this quickly. So this is x minus 3 times x plus 3 equals 0. So our solutions are 3 and negative 3. This is our vertical asymptotes. So this is like x equals negative 3 is a vertical asymptote. And x equals positive 3 is a vertical asymptote. There's two of them here. Horizontal asymptotes, because our degrees are the same, 2 and 2, we look at the coefficients, so 2 divided by 1, and we know y equals 2 over 1 equals 2, is the horizontal asymptote. So this is a great example that a calculator is helpful. Plugging this into the calculator, making sure we have parentheses around the numerator and denominator, and then letting the calculator build a table for us, because when we build this, we need to have points left of this asymptote to figure out where this branch is at. There's going to be a part of the graph that's between the two vertical asymptotes. Then there is a part of the graph that's right of the asymptote. So you split it into 3 sections by the vertical asymptotes. And so if we actually find the points from the calculator, these would be the values you could find. And if we plot them, so this would be the shape of this rational function. Okay, last example here. Now we have the degree of the numerator is bigger than the denominator, so it's a different kind. Finding the x-intercepts here, again looking at the numerator, so to figure out where we're going to cross the x-axis, we set our numerator equal to 0. And so we have x squared plus 3x minus 4 equals 0. We need to factor this with x minus 1 plus 4. And so we have x equals 1 and negative 4. Now notice we're going by 2's here on the scale. So this would be negative 2, negative 4. And the 1 would be right here. Those are going to be x-intercepts. Vertical asymptotes is found by looking at our denominator. So we have x minus 2, so x equals 2 is the vertical asymptote, which would be, we're going by 2's. So right here, horizontal asymptote, because the numerator is bigger than the denominator, then I know that there is no horizontal asymptote, but because it's bigger by 1, because x squared is bigger than x by 1, there's actually going to be what's called a slant asymptote. And to find the slant asymptote, you actually need to divide this out. Divide these two polynomials. So if I take these slant asymptotes and actually divide it, remember long division. You can do long division. Now you could use synthetic division here because we're dividing by x minus 2, but I want to go through long division in case you ever need that for we're dividing by a bigger degree in a denominator. So then x times x would be x squared. So then I multiply through x times x minus 2. I get x squared minus 2x. Let's subtract our two equations. So we get 0. 3x minus negative 2x is actually 5x. Drop the next number, negative 4. X times 5 would be 5x, so plus 5 here. Distribute through. 5 times x is 5x. 5 times negative 2 is negative 10. We're going to subtract those. So negative 4 minus negative 10 is positive 6. Can't multiply x, so my x by to get 6, so this is our remainder. So remainder is 6. Now when you do this, the part of the problem is not the remainder. This is actually the equation of our slant asymptote. So y equals x plus 5 is a slant asymptote. So if I go up to 5, it's my y-intercept. My slope is 1. So up 1, right 1, up 1, right 1. We're going by 2's in the scale, so up 1, right 1. So there's our slant asymptote. So then we can plot some points. We can plug in our values here again into our calculator. Our calculator will help us out. You should see the shape of it on the calculator. But using our asymptotes, it's going to do this. And the other curve, using our asymptotes and the points we plotted, do something similar to this. So there's the two branches for the rational function using a vertical and slant asymptote. Have a good night, and we'll see you tomorrow.